Welcome to tonight's astronomy talk. Just a general reminder for everyone to please wear your mask unless you are medically exempted. Tonight, we are very honored to have Dr. Cosimo Inserra from Cardiff University with us to give a talk titled Supernovae, Origin, Extremes, and a Future Bursting with Potential. Before we begin, here's an introduction about our speaker. Dr. Cosimo Inserra is an observational astrophysicist working on cosmic explosions called supernovae that characterize the death of a star. His current research focuses on the brightest supernovae explosions, usually referred to as superluminous supernovae, and they're used as a high redshift probe. He is also interested in astronomical transients reaching their maximum light before fading soon after, usually referred to as fast transients. He is also working on the implementation of machine learning techniques to transient astronomy to classify and categorize different kinds of supernovae and extreme transients. He has been recently awarded the 2021 Merit Prize as the best early career researcher in observational astrophysics for the investigation of the extremes of stellar explosions, providing a pioneering contribution to their understanding and their role in astronomy and astrophysics. Now, without further ado, Dr. Cosimo Inserra, please. You can take off your mask.
Thank you very much, everyone, for having me here. It's going to be a pleasure to talk about the things I actually enjoy the most and the love, which is, I'm fortunate to be actually my line of work, which are supernovae. So supernovae are the catastrophic death of a star. And that was the first thing that actually tricked me when I was a young student. When they said death of a star, I thought they were going to talk about the Death Star of Star Wars. And I thought, oh, that's brilliant. Sign me in, I'm going to do it. And then I discovered it was actually science. And it was, at the end of the day, it was even actually much more fun than Star Wars itself, which I'm still a huge fan. So the talk of today is going to divide in these 4 chapters over here. And I'm going to introduce you to the supernova event and then go to a little bit further about the extreme of the supernova, the stellar explosion, and how we can use them to probe the evolution of the universe. So the first chapter is about supernova event. One of the first recorded supernovae in history, not the modern, but it's still one of the for which we have the annals, is the supernova in 1572, which is also known as the Tycho supernova. In fact, Tycho Brahe in 1572 wrote the Nova Stella, which saw the explosion of a star in the sky, and he wrote a scientific compendium about that. And the supernova of 500 years ago now is what is called a supernova remnant. And that is a combination of optical and X-ray images coming from the same supernova. Tycho Brahe was also actually the embodiment of how quirky can be astrophysicists, both nowadays and at the time. Tycho Brahe, as you can actually see from these old portraits, had a different nose than any other human being had, a gold nose. He had a prosthetic with the gold nose, and he was living in a tower, and as a pet, he had a goose. So it was very, very interesting character, and that is actually the issue for a lot of modern physicists and astrophysicists. We do all have our quick side, and we actually are all very proud of having it. So that was one of the first discoveries of supernova event back in 1572. But the very name of supernova was coined in Pasadena in the US by Fritz Zwicky and Walter Baade in 1934, because they found a new star exploded in the sky. They found a source that was not there the day before, and they realized it was much brighter than a normal nova event. And then they called supernova because it was brighter than the nova event. To give you a little bit insight, the main difference between supernova and nova is not only the brightness. A nova is a cataclysmic event. It happens when you have a white dwarf and another star. They could actually, the white dwarf, it attracts material from the star, and it creates little bursts, which are going to be repeated in time. It means cataclysmic. Catastrophic means it happens only once, and that is the disruption. So supernova are explosions, novae are instead single bursts of energy happening with a certain period. The other thing that actually divided the supernova from any other event is that they were very, very bright. So in terms of astronomical information, they say we have a magnitude of less than -13. So To understand what the magnitude is, you have to get into the mind of an astronomer, which have no respect for physics whatsoever. So whatever we use in physics, take an astronomer, we are going to use completely different units of measure just to mess up with people. And that is going to be much nicer from us looking smart for a completely different system. So a magnitude is basically a logarithmic 10 scale of the flux, of the energy emitted and the luminosity emitted by astronomical sources. Not happy with that, we devised two different kinds of magnitudes. The upper magnitudes, which is what we get from the stars, what we can observe, which is basically the flux, the logarithmic scale of 10. And then we decide, wait, but we have stars, we have astrophysical objects at different scale in the universe. How we can compare all of them if they are completely different distances? If you have a light, you have a torch, and you put in front of you is going to be that bright, but if you step back of 25 minutes, it's going to be much dimmer. So how can you compare all of them? So you put that at a certain distance of megaparsecs, and that is what we call absolute magnitude. So if we put all these objects at the same distance, is what we call absolute magnitude. But the show is not over. The other things that was interesting is the lower is the number, the brighter is the object. So a very bright object in astronomy has an absolute magnitude which is negative. And the more negative it is, the brighter it is. So if you put the sun and the supernova at the same distance, the sun will have an absolute magnitude of roughly 5. A supernova, to be classified as a supernova, has to be a magnitude which is less than -14. In mathematical terms, those are almost 20 order of magnitudes of difference in terms of flux. So 10 to the 20 of difference in terms of energy and photons released. Just to give you an idea, the sun nowadays can release 10 to the 33 ergs per second, which is unit measured in terms for energies. Supernova is 10 to the 51, so it's basically almost a factor of 20 that I said before. Basically, a supernova event in terms of energy release in one single supernova event can power the entire electrical appliances on our planet for 10 to the 32 years. So far longer than how our planet is destined to live, basically. So that would have solved a lot of issues and problems. The only main issues is how to harvest this kind of energy from explosions. But that is beyond the talk, this talk. So why supernova are important? Okay, first of all, important because I like them, so those are important. Second of all, it's just because they produce iron. They are the only way you can produce iron in the cosmos. So we are here on our planet because a supernova event happened billions of years ago, creating all the imprints, all the elements that have formed all the planets. Iron elements, elements from the iron peak, so all the metals that can be only formed, and something which is heavier than the metals can only be formed during a supernova explosion, because you need very high temperature, very high density you can only have in these cosmic explosions. And of course, you can also create gold, and that is true. You have gold production. Gold can be produced only in supernova explosion, and what we found here is on our planet is a byproduct. And I always say this about gold because that was actually a good excuse to actually have Google funded a lot of studentship across the entire Europe for the search for gold coming from the stars. That was actually the title of the research. As I said before, supernova is seed of life, because without the elements that are producing the supernova explosion, we cannot have rocky planets like our planets, which are able to have life on it. However, as you can also imagine, since our catastrophic explosion, they can be very dangerous. So if you end up to have one of these kind of supernova explosion, which I'm going to show you in a little bit, these are the main two different channels of supernova explosion. These are called thermonuclear and these are called core collapse. And I'm going to show you in a little bit. If you have a thermonuclear explosion, it can actually destroy our planet if the star that exploded is closer than 1,000 parsecs. However, a core collapse supernova is less energetic than that, so it has to be much closer to actually destroy our planet. Spoiler alert, there are no such a star which can explode as one of these two supernovae in this proximity. So from this point of view, we are safe. As I always say, I think the humankind is going to be able to destroy our planet far earlier than anything coming from nature. So the other good thing the supernova, I said before, the 1572 Tycho remnants, Tycho supernova was actually one of the first recorded in European history. But if you go to the Chinese annals, you can actually have the first information about the supernova around 1054, which actually created the Crab Nebula. And there are also information about the Cygni and the Lupus. With the first recorded times, it was during Babylonian time, it was recorded as the Taurus supernova. So this because they were all galactic or very nearby supernova, which could have been seen with naked eyes in the morning close to the sun. So you could see actually another source of light, not comparable to our sun, but very bright in the morning sky for years, basically. And it is why they were recorded. However, one of the most important events in supernova history, in terms of modern supernova history, happened in 1987, when the supernova 1987A exploded in the Large Magellanic Cloud, so basically the backyard of our galaxy. That was the star, which was called a blue supergiant, that was taken 5 seconds before the explosion. This is 5 seconds after. So that was a star exploding as a supernova, releasing all the energy that I showed you before. That was actually the birth of modern astronomy, because it started another gold rush in terms of acquiring information about stellar explosion. And this is actually how supernova 1987A is today. This is coming from a combination of optical X-ray region. So the supernova it was in the center here. So these all the gas has been colliding with previous material expelled by the stars, and they're creating this ball reflectance shock, with basically these energy shocks that have been far apart, like this kind of a cat's eye configuration. So this is now still, technically speaking, is a supernova which is becoming a supernova remnant. Usually it takes hundreds of years to be all the gas far apart, to be so low density that it becomes a supernova remnant. Just to give you an additional information, I said about 1987A, because the custom nomenclature by the International Astronomical Union to classify and giving an ID and identifications to supernova is the SN for supernova, then the years, and then the letter. A means it was the first supernova discovered in 1987. The second one would have been 1987B. Just to give you an idea, nowadays we use 3 letters. So the first one discovered in 2022 was 2022 AAA. We plan by the end of 2023 to have the necessity to use 6 letters because of the new improvement capabilities I'm going to show by the end of this talk. So what is again a supernova event? Okay, we saw as a catastrophic explosions, we have these amazing energies, but there are 2 main channels in which you can force a star to explode. The first one is thermonuclear. So this happens when you have a binary system with specific stars, which I'm going to talk to you in a little bit. The other one is a core collapse supernova. In a core collapse supernova, you have just one single star, which eventually will end up its life, and it will explode as supernova. And I'm going to show as well when this is usually going to happen. As you can imagine, this is a binary system where you need 2 stars, but one of these 2 stars has always to be a white dwarf. While for the core collapse, you have a variety of different stars which can explode as a core collapse. In this figure, you cannot actually see, but there is a point over here, which is our sun, which just to show you the scale of the size of stars which can explode as supernova. So the first one of these 2 methods of this channel of explosions is called thermonuclear supernova. And that is happen when you have a white dwarf in a binary system with a companion. The companion is usually a red supergiant. The white dwarf is the end part of the lifespan of a normal stars, which was as our sun, and ended up as a white dwarf. White dwarf is one of the what are defined three compact objects in the universe. The other two are neutron stars and black holes. A compact object is basically a star very, very compact, very, very small, smaller than our planet, on the size of, for example, the United States or Australia, which has a lot of material, so has very, very high density. Our density you cannot produce in the laboratory, you cannot produce on our planet, and you cannot produce it anywhere else in the cosmos. However, white dwarfs, since they reach the end of the life, there is nothing over there that is going on, is calm, is steady. White dwarfs are paradigm of stability. If left alone, they will stay as they are for the rest of the life of the universe. The universe can go completing the big freeze and getting all the stars far from each other. The white dwarf is still staying as a white dwarf because it is in a specific swift spots where there is nothing you can change. There is no physical mechanism you can change, unless it has a companion, it has a buddy. And because the white dwarf has all these compact systems, they're very, very small, but instead you are very, very dense. That basically means they have a very huge gravitational potential. If you have to manage a gravitational potential, you always have to think about a fisherman net. You put a fisherman net and you leave balls on the fisherman net. You will actually see they will create a little curve. The heavier is the ball, the deeper is going to be this curvature. That is this curvature is basically the gravitational potential. A white dwarf has enormous gravitational potential. And if it has another star like a white supergiant, which is rotating close to the star, is basically going to acquire, is going to take the material from the other star. And this material is going to on the top of this white dwarf, and eventually the white dwarf is going to have too much of this material and say, okay, that is as much as I can take it. And we will basically trigger a nuclear reaction because there's too mass and the white dwarf is not able to withstand all this mass anymore. And it will basically trigger a fuse and it will explode. The white dwarf will explode due to the nuclear reaction. This is what is called a thermonuclear supernova. And that is actually a supernova exploding. A supernova itself has the same luminosities of an entire galaxy. Just to give you an idea, galaxies are 10 to the 30, 10 to the 40 stars, and one single exploding star emit the same luminosities of an entire galaxy. So how does it happen specifically? So when you have these two stars, the white dwarf start to actually get all this material coming from the companion. This material is going to increase the size and it will form kind of a ring inside outside the white dwarf, because you have to imagine these two stars, they're spiraling each other. So all the material will pass to one point, they will start to spiral and stay on the white dwarf in a sort of disk. This additional material will trigger some instabilities from the composition of the white dwarf. It's still unclear if this instability happens on the crust, so on the surface, or inside. But as soon as the instability happens, the entire white dwarf gets destroyed and explodes as a supernova. The other way, instead of having supernova explosions, are the core collapse supernovae. Here you can actually see a snapshot of a supernova we actually, a team I was part of back in 2013 found this supernova. That was the image one day before of the group of stars, and that was the image the day after. And it was in M51, which is the Whipple galaxy. So what happened for this kind of core collapse supernova? Those are basically a gravity stream. Any star which goes up is like our sun. It tends then to evolve. You have to imagine our sun is in the childhood. He's in the middle life of his lifespan. It just came out from puberty, and let's say it's the equivalent of 19 years old. That's our sun. So, and then it will at a certain point, the sun will become over 50, 60s, and it will eventually go to the later part of his life. And a lot of stars, when they go to that part, they start to get bigger and bigger and bigger and bigger. But however, there are so many other stars. There is a huge variety of stars. But what they all have in common is that they have the same elements. They have hydrogen, they have helium, carbon, nitrogen, oxygen, and so on until the iron elements. In all these stars, what you have are nuclear reactions. So each single element from the lighter to the heavier is going to form always the companion that is going to be heavier. So from the hydrogen, you will get helium, the carbon, nitrogen, oxygen, and so on up to the iron, which is the most heavier element you can create in stars. When you create elements by nuclear reaction, what you have is, as a byproduct, is release of energy. This energy goes also by release of pressure, nuclear pressure. So what happens in every single star, even in our sun, in the same moment we're speaking, this is what's happening. All the layers of the star are trying to go to the center because of gravity. It's ourselves. I'm standing here because, not possibly destroying the microphone, because of gravity. I'm actually attracted to the bound. I can jump, but I will always come back because of gravity. The same goes for each single atom, each single layer in a star. It's trying to go to the center. But differently from our planet, there is no, I do not have, here we have a rocky side, we have our ground, and we cannot go further and further down. But stars are just gas. So what prevents the gas to go to the center? All the gas, the nuclear pressure. The nuclear pressure by creating new atoms. So the nuclear pressure is pushing all the elements from the center to the outside, and the gravity is pushing all the elements from the outside to the center. That's a perfect balance for the entire life. Until at a certain point, the stars will finally finish to produce elements. All the elements as there are produced. I do not have any more feeding material, and then the nuclear pressure will eventually stop just in an instant. As soon as it stops, the entire material in less than 0.3 seconds is going to collapse in a single point. As soon as it stops, it's less than a second to collapse everything. We are talking about stars which are even 30 times more massive than our sun. So that is a lot of material in one single point. And because of energy has to be conserved, is one of the beautiful things of physics in our universe. There are low conservation. You cannot produce energy and lose energies if there is nothing in exchange. It is going to bounce back. So what's happened? All the stars, it goes to a single point, and then will bounce back, releasing all the energy, producing a shock wave, which is going to push all this material outside. This is what's happened in a core collapse supernova. And the core collapse supernova, the only way to produce neutron stars, a black hole. Because when you have this material which is collapsed in one single point, you get to densities and pressure and temperatures so high, they will create a layer of neutrons or even at the same density of black holes. So the material which is expelled during a supernova explosion is the same amount of material of the original star minus the compact object that is going to be produced inside the center of the supernova explosion. It might be a neutron star, it might be a black hole. And that is basically what's happened. Is the description that I've told you right now. The all additional perks you can actually see here from hydrodynamic simulation has been done in lots of places. This one is from my colleague in Germany. These explosions are never geometrically symmetric because despite we can actually see stars like balls, they are not geometrically symmetric. And because nuclear reaction are explosions as well, there's never going to be perfect distribution of these shock wave and this material. It's going to be most like a really bad baked cake, which is just going to go all the ways outside from the team. So this is in terms of physics. These are in terms of explosions. But what about observables? So we are also astronomers. We have to understand the physics, but we have to observe something. So there are two main observables we can take to understand the supernova explosions, what they are, what is the energy budget, what are the chemical elements which has been produced. The first one is called the luminosity evolution. This is given by photometric imaging. Photometric imaging is something like you take your phone, you take your DSLR camera, and you start to take images one after each other of a light. It might be a lighthouse, it might be a torch, it might be just one of the lights here of the lecture theater. If you take these over some days, this is what happened to the supernova. If you take snapshot of the supernova like images and you try to measure the luminosity or the flux coming, that is what all they look like. This is the explosion that goes up, it goes down, and then it will settle to this kind of tail. This is because they're driven by the production of nuclei that are radioactive nuclei, which are unstable, and they can only be created. Nickel and cobalt 56 are isotopes of nickel and cobalt, which can only be created during a supernova event. However, for all of you that are not remember what an isotope is and what it means, it basically means is an atom, like it's an element, but it's in an excited state. And because it's excited, as said about us to release the energy, it cannot be excited for the entire time. And when he's going to release the energy, he's going to release photons. And those photons drives the luminosities. What we see, what's all the things we are not seeing, you are seeing me and this light just because of photons. It just was because how the photons are going to impress to your eyes. And this is why you can actually see all of these. The same things goes for supernova explosions. The luminosity you see is actually the photons coming from this nuclear reaction, because you have these new isotopes created by the supernova explosion that then are too much energy and they are unstable, and they will produce these things here, which are photons. And these photons is the luminosity you see. But each one of these is stable. So in 6 days, all the nickel is going to be transmuted into cobalt, and the cobalt in 77 days into iron, and so forth and so forth. And this is basically all the luminosity evolution you will see during the supernova explosions. What is actually driving these events? So basically, the more massive is the star that is exploded, the longer, the faster is going to be this luminosity evolution. So the more it will last in time. However, the brightness, the peak brightness, is going to be driven by how much of this nickel, which is an heavier element, it can be produced during the supernova explosion. The more the nickel, the brighter the object. The more the mass, the longer the time duration of the object. And remember always, because of physics and how is the chemical composition of all these stars, nickel can never be more than 20% entire reservoir of material in the star. So it can never be more than 20% of the entire mass of the star. So this can never be bigger than this one, has to be always lower. And this is actually how they look like. So each star has a completely different signature. Each star that dies as a supernova event has a completely different signature. We will have star like 9878, which is going to be very, very fast, but mildly bright. And then there's going to be something which is going to last even longer and slightly brighter, or things like they're going to be much brighter, but they will last less because they have more nickel than this one, but less ejecta masses because they are not that large. And then we have very, very bright things which are even 10 times brighter than 87A, which are going to last for longer, and they're also brighter. So that is how we can understand what kind of material we're talking about. But then we need also to understand what kind of elements are in a supernova explosions. And we do that with what is called observational spectroscopy. What basically means we observe the electromagnetic spectrum of the star. An electromagnetic spectrum is like, I think it's called ECG in medical science. As when you get a scan, if you see if your heart and everything else is going well as well, that is the same thing for an electromagnetic spectrum for a star. Basically, here you get the energy of the star across the optical spectrum. So what is going to be around blue and violet, around the green area, around the red area, orange, and near infrared. If you see, each one of them has different wiggles and twos. These wiggles and twos are unique signature of the elements of the stellar explosions. So this is what you're going to get. So, and then if you see something like these lines, which are highlighted here in blue, it means those are belonging to hydrogen. So the star that is exploded retain the hydrogen layer. If you don't see hydrogen, you see helium, it means that the star before exploding has already lost entire hydrogen layer. That is just because you have to remember that stars are like onions. They have their shells which are inside each other's, and the one that are on the surface are the lighter elements. So the first layer of this onion is always going to be hydrogen. So if the star has evolved as much that has lost the entire hydrogen layer, the outermost layer is going to be helium, and then carbon, nitrogen, oxygen, and so forth and so forth. So we're looking at these electromagnetic spectra. If we see hydrogen, we know what kind of star was it. If we do not see hydrogen and we start to see helium, we know that it's another kind of star, and so forth. The only difference is that if we see silicon can only be produced in a thermonuclear supernova explosions because of the kind of energy that has been released. So if you see that there is already signatures of silicon and sulfur, it tells you that that's a thermonuclear supernova explosion coming from a white dwarf. If you do not see them and you see hydrogen, helium, or only silicon without sulfur, is actually coming from a single star to core collapse. So each one, as you see, each one, even if you don't get all the fine inputtings, you can actually see that these lines are kind of different from each one. And if you pair these with the luminosity evolution we've seen before, those are unique signatures which tell us what kind of stars are we dealing with. However, as you might have understood so far, astronomers are usually evil creatures. So they tend to confuse and create very complicated things even when they're kind of easy. So they decide to give a very strange nomenclature for all these supernovae. Instead of calling them thermonuclear and core collapse, since we can actually observe things, we do not actually know the physics, we can derive the physics from the observation. They base all their classifications and identifications on the observables. So they devise this kind of evil scheme where all of these things are here, core collapse supernovae, and only this one over here is a thermonuclear supernova. And it is basically based on the elements that are seeing this electromagnetic spectrum or not seeing this electromagnetic spectrum, and so forth. The problem is they decide to call 1A thermonuclear supernova, but 1B and 1C is and 2 and 2B and 2L and 2P and et cetera, et cetera, et cetera. They're all core collapse. So there's absolutely no straightforward to think, oh, I call 1 thermonuclear and 2 and I give 75 letters, but I put 2 and they're going to be core collapse. No, because there's going to be at least some logic behind. They decide to even get cross and using the 1B and 1C for core collapse. But this is showing you that on top of the two normal mechanisms, there is a third mechanism, which we haven't seen before yet. We haven't actually found it, which is called Perseid supernova, for which all the theoreticians agree on. And they're basically very big stars, 500 times the mass of our sun, which explodes by annihilation by pair production. So it's proton versus antiproton that are going to create the destruction of the star. However, we haven't found them yet, which is fantastic because there is only one case in the entire history of science where all the theoreticians agree on what they look like and the observers say, oh yeah, sure, but we never found them. So get back and redo your analysis because we're still not finding them. But we start to find very luminous supernovae, much brighter than these two, and supernovae which are interacting with the medium which is outside the star. If you remember before, I said that some stars have lost the hydrogen layer, the helium layer. But what happens if those stars then explode? At a certain point, all this material which is ejected into the cosmos will catch up with the material expelled by the star before, because the star expels the material with 10 to 100 kilometers per second, which is pretty fast, right? A supernova sends the material outside at 10,000 to 50,000 kilometers per second. So eventually, even if there's been expelled hundreds of millions of years ago, we're talking about a factor of 4 faster material. So in terms of 1-2 years in our lifespan, it's going to catch up with the material expelled by the star hundreds of millions before. And colliding, it will create new signatures, which will oversee the original supernova signature. And that is what is called in this interacting supernova. And now you have all you can start to guess what are these extreme of supernovae. So if I have to put all the supernovae into what the astronomers say supernova parameter space, where here you have how fast or broad the supernova light curves might be, and here is the peak luminosity. Here, this range over here are all the core collapse supernovae, and here are all the thermonuclear supernovae. So it's a very, very small space if you take any kind of number you can find. And we were bound to find something which was not in this region, because we're getting many more data by year after year because of the improved capabilities of our telescopes. And this is what's happened to be the scenario nowadays. So we're set to find a lot of objects which are much brighter and with longer timescales, which we call superluminous supernovae, and objects which are a huge variety of luminosity, but are very fast, less than 10 days, to go up and go down. So much faster than any supernova. And then we also found the counterparts, the visible counterparts of gravitational waves, which is basically the two neutron stars which are going to collide each other, which is called a merger of two neutron stars. Just to give you an idea, the gravitational wave counterparts from the happening of the gravitational wave emission to the peak of the what is called electromagnetic counterparts, so visible in the optical, it took less than 24 hours. It took 17 hours to reach the peak and fade. And in 17 hours, the astronomers were able to move more than 20 different telescopes to observe it. So this is impressive. So what about these? Can these be explained by the thermonuclear or core collapse supernova? No, they cannot. So that's what they say. Okay, I like Star Wars, but this is really much fun. That's the universe is always able to surprise us. As soon as we think, okay, we kind of figured out how stars explode, we start to think all kind of stars which stays on the top of these two layers, which are the physical limits to have core collapse or thermonuclear supernova explosions. So everything is on the top of these lines. You cannot explain with standard physics. It has to be something else. And as you can see, all of these superluminous supernovae, 90% of them, they're over there. So there has to be some new explanation. But before we go to that, I thought that I should at least pay credits to these electromagnetic counterparts of the gravitational wave merger, which goes by the name of kilonova. You might have read some articles, some science stories. It's kilonova because it's not as energetic as a supernova, just kilo, so a little bit, a factor of 10 less. And the important things of the spectrum is basically he created technetium and cesium, which are very specific elements where we were never observed in the cosmos. We have on our planets, and we never observed in the cosmos. We had an idea how they could have been produced, but we never saw them produced in the universe. So they were there, we are on our planets. There was no physical happening in the universe, which actually we observed. Let's say, yes, these are the right physical properties to create these elements we have on our planets. So, and this had happened that the only things you can create these are neutron star mergers. So you can create these in some kind of supernova event and neutron star mergers. However, in supernova events, the percentage, the abundance of these elements is not very high. All the other elements are much higher in abundance, and this is why they are more visible. And this is, but they are the most highly produced elements in the kilonova events, which is the gravitational waves merge events. And these two lines you see over here, the black is the spectrum of these kilonova, the red is a model. And you can actually see that these two leaps over here, they can only be produced by cesium and technetium. And that these are the fine inputtings of these elements, which are actually produced in our universe. So from the low luminosity back to the super luminous luminosities. So these are supernovae, which are 5 to 100 times brighter than any other kind of supernova we ever discovered. We found them for the first time in 2010. And since then, as always happens, if you know what you're looking for, you start to find many, many more. And since then, we have found 180 of these guys. They're all much brighter, they last much longer. And interestingly enough, they all happen in low metallicity environment. What does it mean? We usually define the metallicity of our galaxy as 1. With metallicity means the abundance of metals, how many metals you need to create life, to create new stars, etc., etc. The small and large Magellanic Clouds, which are the 2 our satellite galaxies, have lower metallicities because there's been not enough supernova producing stars and producing these metal elements and so on. So if you look further away into the universe, which basically means you're going to look back into the cosmos like a time machine, you are going to see galaxies which have lower metallicities because those that didn't have enough time to create several layers, several population of supernovae, and then enrich the material with metals, enrich the galaxy material with metals. The further you look into the universe, the further you look in distance, the further you're going to look back in time, because the speed of light, although especially fast, 3,000 kilometers per second, it is finite. If your object is 900,000 kilometers away, a photons emitted by that star, it will employs 3 seconds to reach to us. So basically, we are seeing information which are 3 seconds old, and it goes if you go further and further and further. So these are actually all happening in environments which are similar to the one of the first generation of stars. So they might be the outcome of the first kind of stars in the first supernova, but we do not yet so far for sure. But the things we are starting to be day after day more certain that they are then luminous because they are powered by astrophysical objects called magnetars. These magnetars are very fast spinning neutron stars with a magnetic field of 10 to the 14 Gauss, which you might say, okay, 10 to the 14 sounds really big numbers, but how does it compare? The magnetic fields of our planets that you use for the compass, that the birds use to actually orientate themselves for the migration, is 1 Gauss. This is 10 to the 14 Gauss. So is there anyone here is a fan of X-Men? Okay, no, so 1, 2, okay. So this is the magneto of the stars. So it's the same things. It's a very powerful magnet. And this magnet is producing extra energy that it drives the luminosity of the supernova. And it's why they are so bright, much brighter than anything else. They are normal stellar explosion, but they have an extra kick of energy coming from the remnant. It has to be this specific kind of remnant, which is called magnetar. But yeah, this is not sci-fi. There are 23 magnetars in our galaxy. They're all spun up. It basically means they're spinning slower than the one required to power these superluminous supernovae. So these is 10 to the 14 Gauss and spin. So it creates an entire run in 3 to 5 milliseconds. So it's an entire star that rotates in less than 10 milliseconds. But another important thing you could do with supernovae is cosmology. Cosmology is the study of the evolution of the universe. It will tell us how the universe has evolved from Big Bang to nowadays and why. So the things that came up back in 1993, Phillips came up with this relation, tried to use thermonuclear supernovae as a standard candle. A standard candle in astronomy means an astrophysical object of which you know the luminosity, the intrinsic luminosity, so as you are in front of this object, and you can know a relation of which you can standardize all the family of these objects as they were only once. As you have a prototype object and you have a relation, you can make all the thousands of objects you see like your prototype object if you know one mathematical formula. And that is the mathematical formula he found. So he found a mathematical formula which tells that the duration of the luminous evolution of this thermonuclear supernova is proportional to the decrease in luminosity. And this way he was able to use all of them and standardize all of them. And if you know the intrinsic luminosities, what you could do is you can measure the distance. Because you know how much it should be bright, how much brighter it should be. And if you say dim, if you look at it is dimmer and dimmer and dimmer, you can basically figure it out how far it is. As with a lighthouse, if you're in front of a lighthouse, it has certain kind of luminosity, but the further you go from the lighthouse, it's going to be dimmer and dimmer and dimmer. But the light emitted by the lighthouse is always the same. It's your perception. And the same point, you can, in this way, you can measure the distances. By the time passes in the 90s, Solpermutter, Brian Smith, and Adam Rees found even a better way to standardize them with a thing that's called stretch factor, which basically tells you how big or how elongated is the luminosity evolution. And for this reason, in 2011, the three of them won the Nobel Prize in Physics for the discovery of the accelerating expansion of the universe through observation of distant supernovae. Okay, but I told you that that's the use of standard candle. What is all this blabbing about accelerated expansion of the universe? How did they use them? So this is how they use them. So this is called in science an Hubble diagram. Hubble, it was a famous scientist who was actually, it was studying the evolution of galaxies, and he was actually observing how the cosmos evolves. These two elements over here, Z and mu, are basically distances, but this is given observing, calculated to the velocities of the recession of the galaxies, one from each other and those from us. And this is actually the distance calculated from luminosities. In a plane cosmos, with no evolution whatsoever, you would see a straight line. So basically a one-to-one relation, a diagonal. You would measure the same kind of distances if there was an expansion in terms of dynamics, or you would see photons. However, what we observed, it was these curves. And if you zoom in this curve, which is this area over here, different lines are different evolution scenarios of our universe. Our universe is actually expanded, or our universe is just at a certain point expanded at a faster rate, and then is slowed down again. So if we know this distance from the galaxy hosting the luminosity, hosting the supernova, and we figured out the luminosity of the supernova, which we know thanks to the relation I saw you before, because we know now how bright they should be, we can figure out the distance from the luminosities. And then where this point is going to lay over here, which one of these lines is going to follow, is going to tell us the evolution of the universe, because these are distances. So the further you go from here, the more inside the past you're going to look. So these information are information which are billions of years old, and they just only arrived to us just nowadays. They traveled for billions of years. And because of these, where you can actually placing all these dots, and you put all these lines, the lines actually is the closer to the dots is the line that tells us how the cosmos has evolved. And it's why they got the Nobel Prize, because they show for the first time with proper data. So it was not a mathematical extraction. They put all the mathematical models with proper data for the first time in the history of the universe, and saw that the cosmos, after the Big Bang, at a certain point, have a period of further expansion on a further rate, and then it slowed down again. And you can actually see with the lights of supernova, which are the only way to probe them. And this was done with thermonuclear supernova. Well, this is what I've done with a few colleagues of mine, and we published actually last year these data. And we did the same things with these new class of superluminous supernova. And we found that there is the gray dots over here are the same data that I showed you before, while the black dots are these new objects. And you can see here is where we could observe so far the gray. So we are actually getting much, much further. So we're able to explore even further into the evolution of the cosmos, and we can actually check if it is true that it was a cosmos energy dominated at the beginning. So there was no matter dominated. And it is the only way we can actually probe that and see when actually the first matter is going to be created and when the matter is such to be important. So that is going to be the future of the supernovae, and that is the last part of the talk, which are the last few slides, so I'm not going to bore you for a long time at this point. These are the number of discoveries we are getting of supernovae year by year. As I told you before, in 1987, they didn't finish the alphabet. They were something like 1/3 of the alphabet. Now we need 3 letters. By the 2024, we're going to have 6 combinational letters. And these are the dashed purple line is the number of discoveries. That is 10 to the 4th. We're going to get 20,000 to 30,000 non-supernovae discovered per year right now. And to actually understand what kind of supernova, okay, you said supernova, that's a supernova. Okay, but I need an electromagnetic spectrum. So I need a telescope to point at the supernova and get this electromagnetic spectrum. To get an electromagnetic spectrum versus a single snapshot of image, which is like phone or DSLR camera, but a little bit powerful on a telescope, which is usually between 2 and 4 meter diameter, you need an even bigger telescope, which goes from 4 to 8 meter diameter of a telescope, and you need roughly a factor of 50 more time on the same identical source to get the same level of information that you get from a single snapshot image versus the electromagnetic distribution. So, and this is what is called classification of supernova. You need this electromagnetic spectrum. As you can see, that we're getting better by times where we cannot cope with these numbers. So we are being much more efficient where we cannot cope with it. So that is where lies the future. The future lies in what is called machine learning or artificial intelligence. So artificial intelligence is not only the name of a movie from Spielberg, which I think now it should be 20 years old, but it's also an application of algorithms that learn how to predict supernova and how to classify supernova by themselves. You create an algorithm based on some physical parameter and observational parameter. You give them enough information, enough supernova to train them. And then you say, okay, now you can run loose, go to my new data and try to tell me from the single images, I don't need a spectrum anymore because I don't really have the time, even if I hijack all the telescope of the universe and say, from now on, you're going to have all and classify supernova. We cannot do it. We still have a few of them at this point, as of today, which can be unclassified. This telescope, which is the Vera Rubin Observatory, and the survey, which is going to run for the next 10 years from 2023 to 2033, which is called the Legacy Survey for Space and Time, also known as LSST, is going to get us 22 terabytes of data per night, aka 100,000 to 1 million of transients per year from 20,000. It is impossible. Even if you convert all the astronomers to do time domain astronomy, and believe me, they will not do that because each one of us loves what we do. It is impossible. So this is why we're now more and more going towards artificial intelligence to allow us to predict and tell us what kind of supernova are going to be. And this is very important if you want to do cosmology, because you have to tell which one of them is a thermonuclear supernova rather than a core collapse, rather than a galaxy, which is the center of a galaxy, which is producing energy, which is called active galactic nuclei, or anything else. Even stars which are shedded by black holes, which are called tidal disruption events. They're all things that they might look alike at different distances, but they're completely different events. So you need these things to disentangle. And there are a lot of, actually in Cambridge here, there are a few people that are working in artificial intelligence mechanisms to identify the different kind of supernovae. And this is just the last slide, just to show you how important are supernovae, and not just because I'm telling you so, just because they are important because it's one of the first application of artificial intelligence in astronomy. And you'll be amazed, but astronomy is the oldest of the big data science. Because if you go and you want to be a data scientist nowadays, because you like challenges, you're very good at computing, and possibly because you like a lot of money, because they do a lot of money. The things they tell you, oh, they all want astronomers because they're being used to think logically and already have known to actually deal with a huge data set. If you think about this, the largest data sets in humankind is the number of stars even you can see. So that is why it's very, very good connection. Now we're starting finally to get what is defined as multi-messenger astronomy, because with supernovae, we can relate gamma ray burst observation. So we can relate optical to gamma ray, to X-ray, to gravitational waves, to near infrared, to ultraviolet. So that is the entire, and radio. This is the entire electromagnetic distribution of physics, only coming from one single event. They tell us about stellar evolution, even if we cannot see the stars, because we can disentangle the stars of our Milky Way, but we cannot do it either for Andromeda, which is our closest galaxy. We can guess clumps and clumps of stars, but not every single star. But you can see the stellar evolution of the stars in different environments thanks to supernovae. You get to know the chemical enrichment of the universe, which tell us how we arrived over here. You can do cosmology. You can actually, thanks to supernova, you can tell us how the universe has evolved and how we ended up over here. But you can also get how dust in the cosmos is created. The cosmos is full of dust, grain of dust. Actually, the further you observe, the closer you are to the Big Bang, the more dust you're going to observe. And it's still a big question mark of astronomy how that dust has been formed. It's proper dust. It's not as the dust you can have in your house, but it's what is called dust, or silicate or carbon oxide dust, which is something like you can even produce with volcanic ashes, kind of. And then you can also have information about how stars are evolved to the signature of supernova passing to other material at very, very far distances. So these are a few of the things you could do with one single supernova explosions. So in exactly you can see why is one of the topic that has never passed by, has never been underestimated, and there's been a lot of connection with the rest of astrophysics, because it's very important from a global perspective and global point of view. And with this, I conclude the talks. Thank you for listening my blabbing for the last hour. Just to give you an idea, this is the Large Magellanic Cloud. There was a 30-second image with a normal DSLR camera. It's a 200-pound DSLR camera. But this is taken at La Silla, which is a mountain in Chile that is 2,500 meters over the sea. And it's just 30 seconds of observation. So just so you know, if you go out from any building, you don't see anything. You need your eyes at least 5 to 10 seconds that they get oxygenated enough to actually start to get all the stellar and actually able to see. And you can still not see them. You can only see with the camera, because your eyes are not oxygenated enough to focus and get them focus all those stars. And this is neither one of the highest one. If you go to the ALMA side, which is the top one where the radio telescopes, is 5,000 meters. 5,000 meters, there is a rule that everybody has actually brought the telescope. The telescope has been built lower and have been brought over there with huge truck. And you can they were shift of 1 hour. You cannot have shift longer than 1 hour. Otherwise, your brain is going to suffer critical brain damage for the low level of oxygen. So what they did, the first one they went there, they took a picture with the cell phone. And the way back, they were still not able to see it. It was completely black, the picture. And then finally, when they went down to 3,500 and they were inside the building, finally they have enough oxygen to actually see that 5 seconds of a phone, they captured thousands of stars. Because that is the things you have to do to get astronomy. Usually you get very high places, low from luminosity, very, very dry. So that's the main things, and they're basically all in Chile, more or less. Chile, Hawaii, and other few places in the world. Okay, sorry, that was additional thing.
Right. Thank you so much, Dr. Cosimo Inserra, for the wonderful talk. Now we'll move on to the questions segment. If you have a question, please raise your hand. And
There is one. There is something in the chat.
yeah, if there's any question on the chat on the Zoom call, please put it in the chat as well. So yeah, do you have a question?
Thank you so much for the talk. Very enlightening. I have a question on how effectively we can predict a supernova is going to happen. Just the way we can predict when an earthquake is going to happen. So can we tell, for example, that a particular star is going to go supernova through core collapse, for example, within the next month?
No, you can say in the next 1,000 of years. So that's the precision of we have. So the next one is going to happen is going to be Eta Carinae, which is the closest one to get, but it could be 2 days, but it could be 1,000 of years. So that's the problem with the life cycle of stars. It's very difficult to say that they do not work on human beings' lifetime scales or planets' time scales. So yeah, that we don't have that precision.
Right. Over at the back.
Thank you. I'm quite interested that you're able to get some measurements of cosmological parameters from the superluminous supernovae. I was wondering how independent those were of the ones that you get from the white dwarf. Are they built on not white dwarfs, the Supernovae? Are they built in the same distance ladders?
So they're built on the same distance ladder. So basically, each one of these probes is basically piggybacking on the first one, but the physical mechanism are different for which you can standardize them. So, but you still need some kind of lock-Halo redshift for the superluminous supernova. So the superluminous supernova alone, they cannot work, but they need the thermonuclear supernova. So if you plug them, you can have an extension, something like a part 2 of a movie. You need a part 1, otherwise you're not going to understand the entire story.
So presumably you get like similar estimates.
Yes, we get similar, and that's good because it's also an independent way to check that the thermonuclear actually works. But to get more precise, you need to use them together.
Yes, I see. Great.
Right. Over here.
It's more of a fact than a question. That they found a black hole that can fit 3 Milky Way galaxies in it easily, and that was billions of years ago because the light that you see is from many years ago in the past. So who knows how big it is now? So.
Yeah, and you can bet there are going to be even bigger black holes because there is a black hole inside each one of our galaxies. So the bigger is the galaxy, or the older is the galaxy, the bigger is going to be the black hole. So that's fun. That's the best things of being an astronomer. It's going always to be a new things, a new facts behind the corner every other day. So you'll never get bored.
Right, with a question from the Zoom call. What's so special about nickel to determine the luminosity?
Just because it's a radioactive isotopes. So nickel is formed because of the high density. So it's the only way to form, and is basically a byproduct of the amount of iron which is formed. It's formed during the stars. During the stars, you form this nickel. The isotope itself is a very energetic isotope that it cannot live for more than 6 days. And after 6 days, he loses stabilities, and in losing stabilities means he produces energy. He has to release energy. This energy is in form of photons, which are in the optical spectrum, and that is the specific parts why it is important. But because those photons, they do end up in the optical spectrum, is what's driving the luminosity which we observe.
Right. Do you have more questions?
Just following up on the fact on black holes, if you plot the size of black holes, there seems to be a gap. You have these regular sized black holes, then these humongous giants.
Yes.
Do you know where they come from?
So there are several theories, and we are already filling the gap little by little. Not there are many. So there are stellar-sized black holes which can come from core collapse, but then the bigger one, it might be just a collapse of more and more star. And in principle, there are theories that you can even have more than 2 black holes or 2 or 3 black holes that are going to collide each other, and they're going to enlarge and creating a big black hole. And in principle, that is possible because any stars which are close enough, they basically get enough gravitational potential each other, they can attract each other. The same goes for black holes. So one of the black holes discovered by LIGO about gravitational waves, some of the theories just you have the merging of 2 or 3 black holes, and it has happened during several layers of evolution of galaxies and stars. So these are the 2 channels for creating what is called the supermassive black holes and the stellar mass black holes. And all the way to the 2 of them is just a combination of how many they can actually merge together or not. There's one of the theory, but not an expert in the field, and I know there's not the final point on the discussion, as that is always usual in any things in science.
Right. Any more questions? All right, then I guess that's it for tonight. Thank you so much, everyone, for coming tonight, and thank you again to Dr. Inserra for your wonderful talk. Just yeah, so just a reminder, if you want to collect your membership card, you can do that at the back now. And also, we'll be having our AGM in the coming Monday on the 28th. And all QS members are welcome to attend, and or nominate yourself to run for committee positions. So, yep, that's all for tonight. Good night, and hope to see you guys next week.